This is the first lab of a two-part lab about EIGRP wide metrics. This network has 3 routers using iOS series 15. Router 1, Router 2, and Router 4 all support EIGRP wide metrics, whereas Router 3 is using iOS 12.4. This one does not support wide metrics, but only EIGRP classic metrics. So to begin with, all routers are configured to use classic metrics, and gigabit 2.0 is down at router 4. So let's go to the part number 1 of this lab. Action item number 1, validate that routers are using classic metric using the command show IP EIGRP topology. You must notice that the delay is given in microseconds and the feasible distance is the same as the read metric. So let's go to routers, and first of all, notice that this is the classic metric configuration. So we can use this command in order to know if a router is using classic metrics. So this is classic configuration, classic metric configuration, classic metric configuration. Notice that this router is an old, it has an old iOS, and it is using auto summary. So this means that this router will be advertising routes using behaving as classful. So we don't want that. We'll have to negate this command later on. So let's validate our metrics with show IP EIGRP topology. We're going to work with this prefix, and we can see that the delay is given in microseconds and the feasible distance is relatively a short number. Let's see the read. We can see that the metric is the same as the feasible distance. The metric is the same as the feasible distance. Let's go to router 4. So we can see also here that the delay is given in microseconds and that the feasible distance is a short number, and the metric is the same as the feasible distance. Okay, so let's go to action item number 2. Capture packets between any iOS 15 routers, and let's see what we see. Let's capture packets. I'm going to simulate a failure at router 1 in order to send an update. Let's go to router 1. Let's go to loop back. I'm going to negate the address and enter it again in order to send an update. And let's see. This is the update of the prefix. We can see that the updates between routers using the iOS 15, they are sending wide metrics. Notice the delay is in picoseconds. So regardless of what you are configuring on the router, they will always use the wide metric. Notice also that in the hellos, the software version and the internal software version is 12, EIGRP 12. So iOS 15 routers always use wide metrics in updates, even if they are configured with the classic metric. Okay, let's go to action item number 3. Configure wide metrics at router 4 using these commands. Validate with this command. The delay now must be in picoseconds, and the calculations will provide larger numbers. So let's go to router 4 and configure it with wide metrics. So right now it is using classic metrics. So let's erase this configuration and enter wide metrics configuration. This can be any word. IPv4, tunnel system number 1, network. So now, if we issue this command, we can see that the delay is given in picoseconds and that the calculations are larger. So this is the feasible distance now, and notice that the metric in the RIV is different. So we are calculating, we are using wide metrics now in router 4 only. Now, action item number 4, compare the feasible distance to the metric reported in the RIV. Given the RIV can't manage wide metrics, it has to be scaled down. This is known as RIV scaling. Calculate this RIV scaling using this formula. So let's go to router 4. Notice that if I issue show it per route, this metric is not the same as the feasible distance. So this value is the metric that is shown here. So let's copy these values. So we'll have to divide these to see what is the RIV scale. This is one way of doing it for the lab purposes. So we'll have to divide this number. Let's fire up a calculator. So we'll have to divide this by this number. So the feasible distance by metric gives me 128. So the scale, the RIV scale now is 128. Validate this result with this command, and then we'll have to change it with this configuration command. So let's validate it with show IP protocols. We can see that in the EIGRP part of the output, the RIV scale is shown here, which is the value that we just calculated. And we can also validate here that we're using the wide metric system in this router. When we see this, we can see that this router is using 64 bits for the wide metric calculation. So let's change the RIV scale now. Metric RIV scale 255, and then we can validate that now the metric is this value, which is roughly half of this, because the RIV scale went almost double as previously. So let's go to action item number 5. Calculate the wide metric to destination 10.1.1.0/24 at router 4. So we'll have to go into each router and gather the necessary information. So let's go to router 1 and issue show interface loopback 0. This is the bandwidth. The delay is 5,000 microseconds. So this is the bandwidth, and the delay must be given in picoseconds. So it's 5,000 microseconds. We'll have to multiply by 1 million to get the picoseconds. So let's go to router 2 and do the same with interface 50. This is the bandwidth, and the delay is 100 microseconds. So this is the bandwidth. It's 100 picoseconds. So let's go to router 4 and do the same. Show interface 0.10, and this is the bandwidth, and the delay is 10 microseconds. So the bandwidth here is this, and the delay is this. So the summation of delay will be this something around here. This is given in picoseconds. And the minimum bandwidth, we'll have to choose the minimum bandwidth. The minimum bandwidth is this. So we'll have to use this number here in order to calculate this formula. Remember that in order to calculate this formula, you have to multiply by this number, the bandwidth part, and multiply this number by the delay part. This is the correct way of doing it. You don't add this number up and then multiply by this number. You have to do it this way. Remember also that these divisions are integer. They are not using floating point. So you will lose precision here. So this is the, so you have to calculate this. Let's calculate this part first. Let's go to the calculator, and this by the minimum bandwidth is this number. Remember that this should be integer calculations. So now let's calculate this. And then we'll have to divide that by 153, 153. This is the result. And we'll have to add the two parts together plus this, and this is the result of the calculation. The calculation must be done in this order in order to be successful. I'm going to put it somewhere else. This is the metric that we just calculated. Let's see if router 4 says otherwise. Show IP topology. This is the total delay. That is the same as the total the summation of the delay that we just calculated. The minimum bandwidth is this, so we agree on the same values, and this is the feasible distance, which is the same value we just calculated. Okay, it's this one. So in the next part of the lab, we will enable router 3 to advertise prefixes into router 4, and we'll have to deal with this part that is the metric backward compatibility. What happens when one router is using old metrics and new routers have to use this formula in order to calculate the correct metric, or an approximation to the correct metric. So that's it. Let's go to lab part number 2.